Okay, welcome again, everyone, to the final presentations of astronomical observational techniques and instrumentation. Today's talk is given by Jesse Bublitz. The title is The Quest for Exoplanets.
Thank you, Professor Fiker. Afternoon, everyone. I'm Jesse Bublitz, and today I'm going to be talking about exoplanets. Specifically, I'm going to be looking at Kepler data in order to understand just what we can learn about those planets. So I'll be discussing both Kepler and its current iteration, K2, and analyzing what our limitations are for that data. So, I'll give a brief overview of exoplanets, talk about the Kepler system, its current status and state. Then I will go into my attempts to use Kepler and K2 data to look at planet transits. Spoilers. So, what are exoplanets? Well, they're planetary bodies that are outside of our solar system. However, they are also quite far away. It was actually just this past month published. The closest exoplanet currently found is 39 light years away. Its name is GJ 1132b. If that means anything to any of you. But what I'm trying to talk about here is the fact that exoplanets are not only quite far away from us, but they're also very small in the grand scheme of other cosmological objects, which does pose a lot of problems in trying to detect them. For instance, our only method of actually finding these exoplanets is from when they cross in front of their star and dim the light. This is a planet transit. And typically, for a relative flux of their star, they will only cause a dip in about 0.2 to 0.5%, with large Jupiter-like objects sometimes getting up to 1% of light decreased. So, why do we even want to look at exoplanets if they're so far away and so difficult to see? Well, because of that fact, we're not going to be able to go to any of them anytime soon. So we can at least look at them, or whatever information we can find, to get a better understanding of our planet. Now, we're the only ones, we're the only planet that we know of that has life on it. So we can't go around asking what other planets are like, how they formed, what is the most likely type of planet out there. Are we particularly unique, or are we actually quite common? By getting surveys of all the exoplanets out there in not only our galaxy, but in the universe, we get a better understanding of that. And of course, get a better understanding of how likely is it that there is life on other planets. Do aliens exist? I don't know. I'm not going to be talking about that here. Instead, I'm going to be talking a bit about one particular type of data, and that's through the use of Kepler. There are other telescopes and missions out there, including SuperWASP or Cora, which are quite familiar. In fact, a speaker tomorrow is going to be discussing planets found using KELT. But, as I said, I'm going to be focusing on Kepler and its current iteration, K2. Now, Kepler is a 0.95 meter diameter telescope, which was launched in 2009. To this date, its data has managed to confirm 1,031 exoplanets, while the K2, which I'll discuss the distinction later, has confirmed 32 as of this past month. So, as I said, Kepler was launched in 2009 to detect Earth-like planets in the Milky Way. It was designed to look, to orbit in an Earth-like orbit and to look upwards at towards the galactic plane at one very particular region. So you'll see here at the top we've got the aperture of the telescope, and on the left side, going around through the back, are a bunch of solar panels. Now, how Kepler works is that it would align itself with solar panels facing the sun, that is ideal, and using 4 thrusters, or reaction wheels as they refer to them, it would continually reposition itself as it moves around the sun, always looking at that one particular region. Now, another interesting feature about Kepler is that it has a 115 square degree field of view. This is significant compared to Hubble's 10 square arc minutes, which is about 0.0028 square degrees. So Kepler has a very large viewing area in order to encompass this whole region of the Milky Way that the Kepler team are hoping to be able to find all these planets in. Unfortunately, in 2012, July 2012, one of the reaction wheels failed. Now, this ordinarily wouldn't be a huge problem, except in May of the following year, a second reaction wheel failed, leaving the Kepler system with only 2 thrusters in order to keep itself properly positioned, which it is not able to do with respect to solar radiation as it goes around its orbit. So the Kepler team faced a huge problem, and they were considering whether or not they could even do anything more with the program. When, fortunately, in 2013, they managed to come up with an alternative system in order to make up for the fact that it only has 2 reaction wheels and is constantly trying to counter imbalances by solar radiation pressure. Now, they called this system K2, second light. So the way K2 works, that is different from Kepler, is that instead of looking up in the galactic plane, it is looking down along the ecliptic plane of the sun as it orbits. And if it were to stay in this position for an extended period of time, as you can see here, it would go up to a point along its orbit that would be looking straight at the sun, which is not good for the optics of the system, and also means the solar panels wouldn't be getting any more energy. So in order to deal with this problem, they've broken up the orbit into 4 quarters. So for each of these quarters, they'll be looking at one region of the sky, and once they've gotten to a point too far along the orbit that they risk losing energy, they reposition it and look at another region, going around looking at a different location in the sky every quarter. And through this process, they're using the 2 remaining reaction wheels to balance out any pressure that is being caused by the solar radiation. And you get all these regions lined up here. So we can see the different campaigns that have been planned out for K2. Just recently, they released data for campaign 5, which is right here. They're currently analyzing campaign 6, and they're collecting data for campaign 7 right now. But what kind of data are we going to be getting from this new system, now that you're limited to only 2 reaction wheels? Well, it turns out there's actually a problem with this. As you can see in the plot at the top here, this is a plot of the relative brightness of the star EPIC 6002146, which does not actually have a planet transit, but it is meant as an example star captured by Kepler's campaign 0. So you can see here that there is still a lot of noise going on, but what exactly is causing it? If we look at plots of the centroid of the Kepler telescope in the X and Y position, you'll notice there's this sawtooth motion. This is actually caused by the thrusters. So in each of these downsloping regions here, you'll see is caused by radiation pressure slowly moving the center of the Kepler telescope off of its position. And so every approximately 6 hours, they have to correct for this with thruster fire using those two remaining reaction wheels, which are these sharp motions here. And if you'll notice, they correspond with the noise that's shown here. So Kepler is constantly having to realign itself in order to look at one of these regions for any given campaign. And this jittering motion from the sudden use of the thrusters is a significant problem, because you'll notice for this star in particular, you've got change in relative brightness from this noise of about 0.2, 0.3%, which is of the same order as a standard planet transit. And in this case, thanks to the work of Vandenberg and Johnson in 2014, who came up with a method for correcting for this, they give an example of planet transit for Kepler 10b, which has been injected into this star. And you'll notice that without their programming, you might not be able to tell that there's even a planet transit in there. So what is this method that they managed to use? They call it the self-flat fielding correction method. You know what this is? The blue data you see here is the same as from the previous plot. So in order to correct for this, they looked at a couple features. One is they created a mask for this data, which is as Kepler is being moved away from its position, the light, the photons for a particular star that you're trying to look for a planet transit on is falling on different pixels in the CCD of the telescope. And so you're going to get a different signal, slightly different signal from that. So they have to use masking techniques in order to even this out. But the key here, in order to correct for these thruster fires, is to look at the arc length of the motion. So they plotted the flux with respect to that in order to try and weed out this data. And you'll see the dots, the data points marked in red here, are actually a result of this thruster fire. And using their SSF method, you can correct the data down into this nice smooth curve here, shown in yellow. Now, one caveat for this system is that the SSF method does not work on Cepheid variable stars, contact binaries, giant stars with large amplitude oscillations, and logically, planet transits on the order of 6 hours, because they can potentially get lost in these thruster fires. So basically, any star that does have natural variability in it is going to face some issues when you're trying to get rid of this variation. Now, another thing to look at here is the precision. You can see that for the raw brightness data, you have a precision of about 200 parts per million, whereas with the corrected data, it's down to 40 parts per million. But what does that mean exactly? Well, we can take a look at the precision data for Kepler to compare. So you can see that using the SSF method, they've managed to correct raw K2 data around 4 times, which is a significant improvement, although it is still slightly higher than what they had been able to obtain for Kepler itself. This is particularly noticeable with higher magnitude stars like 14 and 15, which still has about twice the precision value as that of Kepler. All right, so once we have a star's light curve, what are we going to do with it? Well, we can begin to correct for these features. We can then look for any periodic variations to remove them and look for the telltale period of planet transit. From there, we want to flatten the flux value, give a relative flux of 1 in order to determine what the depth is. And then using various programs, we can fold these transits on top of each other, producing multiple data points for a much cleaner look at this light curve shape. And then we can start to analyze. Now, here we have some raw data from the star, from the planet K2-21b. Now, I plotted this using Pike, which is a Python program recommended by Kepler, and has many incredibly useful features which allow you to reduce the SSF, allow you to flatten it, and ultimately to analyze the light curve. Now, unfortunately, when it came time to look at this data, I ran into several problems trying to use data like this on the program Pike. So suffice to say, I'm still working to uncover what those issues are in order to analyze the planet transit data for K2. But for the remainder of this presentation, I'm going to be focusing on Kepler data. So as I said, Pike is one of the programs utilized in understanding planet transits. And, well, very useful, especially for K2, dealing with the K2 noise. I instead switched over to using ExoFast, which is a slightly more general program which runs on IDL. And you can also use it for planet transits, but it also works very well when you're including radial velocity data, RV data, which I will discuss a little later. So, for now, I'm going to be talking about the process that I've used to analyze Kepler 5b, which is one of the first 5 planets that Kepler was able to confirm. So, plot above you'll see is the non-reduced flux for the star, and below it is the normalized flux down to a level of 1. The data for this is actually a lot longer, several more light curves, but I've chosen to look just at a small region just so you can see what these transits look like a little bit more clearly. And I notice there's still a little bit of variation in the flux of the star itself, but that is negligible compared to the dip the light curves. So the first thing that you can notice just from these plots themselves is that the dip of the curve here goes down about 0.6%. So we notice we're likely looking at a rather large planet, possibly a Jupiter planet, which once we analyze this, we'll see we actually do have. So once we've normalized the flux, and we can then fold the periods together and fit a curve to this planet transit. From there, we can then analyze various features about it. And here we have that final plot, which shows us our lovely U curve for Kepler 5b. So from here, we can get a lot of things right off the bat. we can determine the period of the planet's orbit using the length of the light curve. And we also know the radius, which is proportional to the dip of the curve. Which is why we want to reduce the data to relative flux, so that we can look at just what a change in the brightness of the star this planet transit produces. So from the dip, we can determine the radius of the planet, and we can, using the period, get at the semi-major axis of the star and planet. And as we'll see here, I ended up analyzing data for Kepler 5b, 6b, and 7b, comparing them with the published results. So, a few things here. We noticed that my data actually came quite close in almost all situations to published value for these three things: period, radius, semi-major axis. One of the few exceptions is the radius for 7b, which wasn't explained by their error. But we can also see that each of these is quite large. They're all actually hot Jupiters. Now, when it comes time to looking at other really useful, seemingly useful information about planets, we notice we don't actually have a mass. So planet transits themselves from a light curve cannot give us the mass or the density from that. So unfortunately, we have to look at RV data, which Kepler does not provide. So using Kepler, we can get a lot of basic properties of this planet, but we need to use other telescopes in order to get mass, get density. You can determine temperature, and if we're really lucky, depending on the ability to see this planet, you can also determine a little information about the atmosphere. But it becomes apparent that we only know so much about these planets. There's still a lot that's missing. And while this might seem problematic in the grand scheme of things, we can still learn quite a bit about our planets, at least in comparison to the broad scheme of the universe. So we can determine are planets more likely to be large Jupiters with predominant gas clouds, or are we going to actually find a lot of rocky planets, possibly in habitable zones? Could they support life? What's the probability of these things? Of course, we can only limit ourselves so much to that sort of information. If you'll remember at the very beginning of my presentation, I provided an artist representation of an exoplanet. And it looks so pretty. It's got this lovely atmosphere, these clouds. You can maybe even make out some continents on there. That's just all speculation. None of that information we actually know about any planet. And we aren't going to unless we produce some impressively large telescopes, or we manage to get that fashion light travel and go out to these places. So, in conclusion, we can get a fair amount of information out of these, but for me, I would like to continue working with Pike in order to understand its full capabilities and figure out how to mesh its system with the Kepler released data packets. From there, being able to compare its ability to determine these values with other detection methods, and actually get an understanding of other features. So, thank you very much for your time. Do you guys have any questions?
Okay, time for questions?
I actually have one.
Yeah.
So you keep talking about applying thrust.
Mm-hmm.
So is it not using the reaction wheels to do that? It's actually burning fuel?
Right, so the reaction wheels are what's causing this thrust.
Oh, so aren't they just gyroscopes that are rotating?
Basically, well, the problem is that Kepler is being rotated over time due to the radiation pressure from the sun. And so all they're doing is constantly correcting and just repositioning what region it's looking at in its orbit.
Okay, but when it makes those big turns, is it actually burning fuel, or is that just the reaction wheels?
I believe it's not actually, it's just using the reaction wheels themselves.
And why, I'm just not understanding, why is there that initial spike? And then, like when you showed that method that did the corrections, it removed some outliers?
Right.
There's a spike.
Alright, so I don't actually know just how the reaction wheels function, but it's evident that they are producing enough push at the onset to cause these variations. The reaction wheels are turned on and rotated for half an hour, but it seems that it gives a significant bump to the telescope itself, that it produces this rather frustrating noise in the data.
So if you go back to the subtle thing.
Yeah.
So
This one or this one?
Yeah.
Yes.
So if I understand it correctly, then the really huge jumps are due to when the reaction will realign the thing. Then the shallow slope is when
It's
the
getting,
reaction wheel is not doing anything.
yeah,
and
it's getting moved off
radiation
course.
just push it slowly.
Yeah, well, my understanding is that the reaction wheels just exert torque on the center of mass, so it doesn't actually move the center of mass of the object, whereas thrusters can move the center of mass.
Okay.
So reaction wheels are for pointing, for pivoting around the center of mass. So what it looks like is happening here is that the telescope is pointing towards a star, and then for some reason there's a torque on the telescope due to radiation pressure or something.
Yeah, so there's, due to the fact that they don't have all four reaction wheels themselves, they're not constantly being used to.
So that using two reaction wheels exerts.
It's possible that I've confused
non-zero torque or
the
something.
use of the reaction wheels with actual physical thrusters, but they are used in tandem in order to help realign this.
Anyway, it's an interesting question. It's really
So basically, as it's moving around its orbit, it's constantly being bombarded by the radiation pressure, which is enough to just knock it off course.
So why is it the case that when the star is drifting, it looks like it's drifting in the focal plane a little bit, a pixel or two? Why isn't it the case that one could define a large synthetic aperture that would integrate all the flux?
Oh, for
regardless of where the star is, like if you made like a 5 arcsecond radius aperture in the image, and whether the star was moving a little bit this way, it wouldn't change the flux. And maybe the answer is that it actually does change the flux a little bit. Because this is small, right?
Relatively, yes.
Yeah, so even if you think all the starlight is in this big aperture, the fact is that there's a tiny percentage out in the wings, so maybe it is changing them.
Yeah,
how big was the aperture for this?
Trying to remember. I don't recall specifically what the value is, but one of the other possible issues is depending on what region they're looking at, the density of stars could be an issue.
Oh yeah,
How much?
because the aperture is big and it starts seeing other stars. Yeah.
So you have to
Or
be really
wings from other stars.
Exactly. So you have to be really careful about deciding exactly what aperture you'd be wanting to look at. You'd have to specify that for any individual star.
Although you could move the center of the aperture to be coincident with the inferred centroid.
True.
So as the star is moving, you can just write the software so it, is always centered on the centroid. Anyway, a lot of questions about that. Any other questions?
Yeah.
Can K2 see Earth-like planet transits? I know that's usually a problem.
Yes, it can, yeah. K2 is actually surprisingly good about that with its precision, despite its large field of view. So it is able to detect Earth-like planets like Kepler 10b, which is a rocky Earth-like planet. But that's the problem with K2 is that they have to really worry about analyzing this noise because of how small they can be. But yeah, hot Jupiters are a lot easier to see. And so those are more often found, especially in other ground-based telescope systems. Yeah.
How long does it actually spend in one field? Because that limits
Yeah. So
orbital period.
K2.
Yeah.
K2 spends a quarter, which is actually about 75 days, looking at one particular region. So while it is a considerable amount of time, it's actually a lot less than Kepler, which was looking at one region of the sky for 3.5 years.
Well, we wouldn't be able to find a second Earth with K2, because you need 3 years to see 3 periods.
Oh, okay. Well, yeah, it depends on what the periods are of those
Right.
planets.
Yeah.
So yes, if we wanted to try and find an Earth-like planet that has a period similar to ours,
Right.
we would either have to get really lucky, seeing just as it happens to pass, and we get one like Earth, which again isn't very.
But doesn't Kepler only determine, they only consider it confirmed if there's 3 transits, I thought.
Yeah,
So,
but it would be enough to consider the possibility, and you could then use other telescopes to follow up.
So I assume that the confirmed planets that we have found so far are not like 1 year period.
Yeah, I don't know exactly what the various periods are, but there are a lot more common to find really short periods.
Mhm.
Like for the first few I analyzed, they had a period of only a couple days.
Yeah, that's not Jupiter.
Yeah, exactly. They're really large compared to a really small star, and they're orbiting really close to their star, which is the ideal for looking at planets, but it's not ideal for looking at planets that might have life. At least that we know of. More? Yeah.
So the correction method, does it work entirely based on the data, or does it also consider, what Kepler itself is doing? Like, does it consider what time it was thrusting, or is it just find that from the data? So I'm wondering if maybe you could see some star that was exhibiting some variability, and if that could misinform the method.
Interesting. Okay. Yeah, so it does. It doesn't directly take into account like the times that the thrusters were being fired, I don't believe. But by comparing it, by plotting it versus the arc length as it moves across the sky.
The arc length of what?
The arc length of the centroid of the star.
Okay.
Yeah, there were some plots of that which I chose not to include in this. But if you'd like, I can show you this after. We can talk about it. So yeah, I don't believe they directly take into account the thruster fire, but part of this method is to look for data as a result of that and use those out.
It seems like they could take it into account somehow. That might be helpful. Because they know when they.
That's
I
true.
assume they know when they fire.
I should look at that a little bit more closely, but it's possible they also are focusing on the period between those thruster fires. Any other questions?
Do you remember what type of host stars these planets were around? Like what kind of star it was? Sun-like, non-sun-like?
Oh, right. Each of these had stars that were approximately sun-like, with some variation. I believe the masses for 5b and 6b were slightly larger. 7b was slightly smaller, and then all of them I think had radii that were around 1.3 1.4 valve for the sun. Right?
I had another question. Should we be seeing a second dip in the light curve when the planet goes behind the star? Or is that not how it works? If the planet's big enough and it's covering the star, it absorbs some of the light from the star, so there's a dip. That's the main dip,
Oh,
right? But as it comes around, you can start getting some light reflected from the planet back toward you, right?
That's true.
So the flux should be increasing, and then an extra contribution should go away when it goes behind the star eclipses the planet.
Yeah, so
there should be like little slopes or something and a secondary dip, or should that not be expected?
for Kepler data, I'm not sure if K2 has the precision to detect those.
But if you go back to one of your curves,
Sure.
So this looks pretty flat, right?
Right.
So we're not seeing a lot of light reflected from the planet back into our line of sight. And then it doesn't really look like there's a dip in the middle.
Right, so, as I was saying, I'm not sure, how well Kepler is at dealing with.
But you can calculate that, right? If
Yeah, you
know
could,
Jupiter.
you could
well,
certainly
a planet.
calculate, what you'd expect the change in brightness to be. So it wouldn't be a dip, it would be an increase, wouldn't it?
Yeah, but
As
well,
you're
the
getting
planet
more
goes in front of the star, there's the big dip, right?
Right.
And then it's off the star, so the light goes back to normal. And then as it goes through its phases, you start to see like a half moon, half planet. And then back here it's a full moon or full planet. So the light's increasing.
Yeah.
And then it goes behind the star.
Oh, okay, so you're saying you get this slowly trending
Yeah.
upwards and then
You
it
get
would
like
go.
this and then a dip here
Yeah.
that I guess just goes back to this level or something.
Yeah, it would be back at the regular. So I guess the question is, how large would those slight increases just before it passes by and just after?
I'm pretty sure I've seen it in data. I'm not sure if it's because I've seen different aspect ratios or mass ratios or something. Maybe
Sure.
this ratio is too big. It's in area it's like 100 to 1, right?
For this?
Jupiter to the sun's like 101 in area, 100 to 1, right? Because
Yeah.
it's 10 to 1 radius,
Yeah.
right?
Yeah, I would say for this one, the primary dip is so huge that it's really difficult to see if there's a second dip. Like,
Yeah, but if you phase overlap, right? The other data were phase overlap, right?
Yeah, unlike your next slide.
Yeah, go to your next slide, it's phase overlap. So you increase the percentage by folding.
Yeah.
And this looks really flat.
also, I don't know if this is the same exofast thing that I used to use, but the one that I used to use a long time ago didn't fit for the second dip, so you always use the U shape.
Okay, anyway, that was my question.
Okay.
Yeah, I think that's it. Any other questions? Okay, thanks again.
Thank you.